Okay, so here's our next one, number 23. So in this case, we've got a 2 kilogram sphere. It's attached to a rod. It's rotating in the horizontal plane. The system is subject to a couple where, determine the speed at the instant. Okay, so uh, again, like the last ones here, we're supposed to try to, in the end, find the speed of this thing. Okay, now let's break it down just a little bit first. There's some code words in here to watch out for. It says light, rigid rod. Okay, so that's a code word for ignore the mass. So some kind of super spectacular material that's infinitely rigid and happens to have no mass whatsoever. Nice. Okay. It tells us a 2 kilogram sphere, but it doesn't tell us anything about how big the sphere is. Okay. So that means we're forced to assume that the sphere is basically a point mass going round and round and round. Okay. Now, if we were building a better model, okay, we would not assume it's a point mass. We would assume it has a certain shape. Okay. And as that sphere actually goes around, it is also turning as it goes. So a better model would take into account the fact that not only is there a circular path, but the sphere itself is rotating as it moves along that path. In order to do that more complicated model, we have to know something about the size of the sphere, not just its mass. And so we're just going to ignore all that and assume this thing is just a point going around and around and around and around. So there we have it. Okay. So define the speed. So this means that just like from before, in the end, what we're going to be looking for is some sort of final angular momentum. And that final angular momentum is going to be a mass, velocity, and a radius. Just like that. Okay, everything is just the same. And just like from before, the real key to doing this thing is going to be to find the impulse. And the impulse is our integral of m dt. Okay. Now, the last time it gave us a force and a distance, and so we had to calculate the moment. This time it just says, meh, something's causing this thing to spin. Okay. So there's a motor or something, a drive shaft that's hitting it like this. Okay. Now, did you notice where it said that this thing is in the horizontal plane? Okay. Did that seem a little odd? Why would they bring that up? Why would they bring that up? Well, that's because as we are looking at this thing, we're looking down on top of it. Okay. So gravity is not affecting this thing at all. If we were to put gravity into the picture, then what we'd have to contend with is the fact that on one side, we've got a moment one direction, but once that thing rotates over to the other side, it's going to generate a moment in the opposite direction. Okay. So it becomes a little more interesting. Okay. But just like in terms of the size and the shape of the sphere, we're going to ignore all that. All we have to do is to calculate what's that impulse value, which means all we have to do is to figure out that integral, mdt. Okay, so our moment, as it's told to us here, is 0.9 t squared. So then we're going to integrate 0.9 t squared dt. And we're operating over a 5-second interval, 0 to 5. Okay, it does say starting from rest, so that's kind of nice. That means our initial angular momentum is 0. That's very handy. If we work out our interval here, okay, we got 0.9. We're going to have t cubed over 3 from 0 to 5. Okay, so I'm going to keep going here. So that's 0.3 t cubed, 0 to 5. Okay, 5 cubed is 125. 5 times 5, right? Okay, So we got 0.3 onto 125, which becomes like 37.5 or something like that. Let me get a number on that. Okay, 125 times 0.3. Yeah, 37.5. Okay, 37.5. Okay. Um, and whoop, sorry about that. So then, just like last time, once we've got this delta right here, we're just going to add it on and figure out then from what our H final is. Okay. H final is going to be that 37 and a half. And then we just work it out. Okay, it's MV final, R final. Solve for V, and call it a day. Okay.